Hello, Advanced Calc students. We are in lesson 6.1, which is the beginning of derivatives and the definition. And I'm going to work through the ICE problems. I'm not going to do all the A through E or whatever for each problem, but you can get the idea. So question 3 is the first one, and it says, make sure you have the textbook out with you, because I'm just going to say the problem. I'm not going to write it out. It says, determine if each function is differentiable at x equals 1. If it is, find the derivative. If not, explain why not. So the first problem is the function is 2x minus 1 for x less than 1, and then x squared for x greater than or equal to 1. And that does match up at 1. It has a slope of 2, and at 1 it's 1, so it kind of goes like this, and then like this. And it's kind of bendy, but I believe it should be differentiable. The limit exists, it's continuous there, so I can try to take the derivative. And so you have that h going to 0 definition. You don't really want to do that here, but because which side are you coming at? But if you think about it this way, you can do the other definition, limit as x goes to 1, x minus 1, and then f of x minus f of 1. Well, you've got to do two different things from each side, but you know what's going on each side. If you go from the right, so we'll go from the right and the left, and we get the same thing. If you go from the right, you're on the x squared side, so you have x squared minus 1 over x minus 1. And then you can cancel, factor and cancel. You should get this, and you should get 2. And then the other side, you hopefully get the same value for the derivative. So that derivative made sense. Let's check on the other side. It's possible that if you, with a piecewise definition that it's continuous, but you just get two different values for the derivative, and then that wouldn't work. So if I do f of x minus f of 1, x minus 1, and then I'm going from the left, so I use the other definition, 2x minus 1 minus 1, x minus 1. That's 2x minus 2, which is 2 comes to quantity x minus 1, that cancels. You're taking the limit now of a constant, which is 2. So because I get the same value, that checks out, and that's the limit. So because they have that limit, remember I'm doing the derivative definition limit, so it's differentiable there, the value is 2. So f prime of 1 is 2. There's too many parentheses there. So that was equal to 2. So that was 3a. I'll do one more of these. So what I just said about getting different values, if you try C, you should try that. You should get right hand and left hand limits. You should get different things. If you look at B, so I'll leave you guys to do C. If you look at B, which is 3x minus 1 for x less than 1, and then x cubed for x greater than or equal to 1. That graph, if you go at 1 from this way, you get 1, but if you go the other way, you get 2. That's not even continuous there because the limits don't match up, so definitely not differentiable. So if you don't have continuity because you don't have a limit, then you definitely don't have a derivative. And then C actually is continuous and hooks up, but you get different values, and so you'll get two different things here, and you guys can check that and show that that's not differentiable. The very mean ICE key says that the next problem is routine, which is kind of mean, but it's something that it's definitely going to be in your test because it's something that we don't hit very hard in Calc 1 here, and it's something that you should know how to do because you might teach it or you're definitely going to use it if you go on to graduate school. So I'm going to pick a couple problems to do, and so I can use, there's two definitions, right? A minute ago I just used this one, f of x minus f of a, f of x minus a. So that's one way to show the derivative. This is f prime of a. Another way to do it is f of a plus h minus f of a over h. Or if you're trying to do f prime of x, this is the limit as h goes to 0. If you're doing f prime of x, then you would just put x instead of a. I tend to like this one better because it's simpler just to cancel the h on the bottom, but both work. So let me do C and D, and then you guys should be able to do the rest. Especially if you can do C and D, then E will be kind of combining those. And then A and B you should be able to do with algebra. So it says find the derivative, so let's do f prime of x equals, so for C, f of x was 1 over x. So this is going to be the limit as h goes to 0, and it's going to be 1 over x plus h, because I'm putting x plus h in for x here, and then minus the regular function over h. So I'll do common denominator up top, because I don't like double fractions. So you get x minus x plus h all over x times x plus h. You get negative h up top, x plus h. Okay, so be careful with your double fractions, but these h's cancel now. And canceling that bottom h is always the point, so now you get this. And now I'm allowed to make h 0, and so you get negative 1 over x squared, which you knew was the answer. The nice thing is you know what the answer is supposed to be. Okay, so d is square root of x, so f of x is root x. And so for f prime of x, take the limit here, h going to 0, x plus h goes in for x, there's the original. So normally you think about rationalizing the denominator, but I'm going to rationalize the numerator here. I'm going to multiply by the conjugate on top and bottom, because that's pretty much just what I do with square roots. When you FOIL the top, you get x plus h minus x, which is good. And then the bottom, you have this h. Do not distribute because you want to get rid of that h. So just leave that like that. Still got the limit here, but after you cancel those, the h's cancel. And then you've got 1 on the top, and then you've got this mess. But now that I can make h 0, those become the same thing. So you get the answer you knew you would, 1 over 2 root x. Okay, so a, b, and e are similar. That's a straightforward problem. It is kind of annoying algebra, but it's an important concept, and look forward to it on your exam. Alright, I think the next problem was 7 on the ice sheet. Yep. Okay, so it's determine for which values of x each function from R to R is differentiable at, and find the derivative there. Okay, so A and C are pretty straightforward. But I'll just kind of show you where these are at, or what these look like. So A here is absolute value x minus 1, and C is absolute value x. And you should know, remember I just talked earlier about the piecewise functions? This is a piecewise function, right? It's x for x greater than 0, and it's negative x for x less than 0. And you get 1 and minus 1 as the two different limits for the derivative here, so it's not differentiable at 0. So f prime of x is 1 for positive or equal to x, or actually not equal to, because there's no derivative at x, or sorry, I didn't, x equals 0. We know that already. So for x strictly greater than 0, you're good, and then for x less than 0, you get that, right? That's the derivative. So it's not differentiable at 0. You have the same issue here. This is shifted over. It's just that 1 is the problem piece. So same idea for A. Okay, so B is a little more complicated, and so is D. This is x squared minus 1 in absolute value. So if I graph that, it should look like this parabola, except it's going to look more like this. I'm not going to have that graph going underneath like I would like for it to. Remember that absolute value is always going to make it positive. So this part's going to go away. And you're just going to get that positive stuff, and you're going to get kind of some corner-looking stuff, which makes me suspicious that 1 and minus 1 are not going to have a derivative. I'm not going to go ahead and prove that, but I'll show you what the derivative should be. It's not differentiable there. Out between minus 1 and 1, it would have been 2x, because that would be the normal derivative, but we flipped it up, so it would be negative 2x. All right, you can tell it's actually decreasing here and increasing there. And then it's 2x like it should be in the everywhere else. And then the last one, D, is x times absolute value of x, which is interesting to think about. So this is x squared ish. So let's think about what this would look like. So when x is positive, that's just x squared, right? When x is negative, this is only one of these is negative, so it actually kind of goes down like this, right? So it looks like x squared trying to be x cubed. And now, the only real concern is at 0. Otherwise, well, certainly for positive x, it would just be 2x, right? And for negative x, it's this. So what about at 0? Well, is the slope still 0 at 0? If you come at it from, so if you take the limit as x goes to 0, let's do it that way, and then f of x minus 0, because that's f of 0, over x minus 0, well, you get this thing, and I don't really need to do this piecewise because those cancel. And I just want the limit as x goes to 0 of absolute value x. We already drew that graph up here. The limit at 0 is 0. So you get 0. So you could either of these would be 0 at 0, so you can just mark it. And in fact, another way to write this in the back, if they just write this as the derivative, which works because the left side is, it's 2x, but you flip it on the left side. So that one actually is differentiable at all x. Alright, so the next one is number 9. And this is another ABC problem. Let's take a look. Okay, so this is actually several parts of the same thing. So we're going to let f of x be x squared for x greater than or equal to 0, but it's going to be 0 if x is less than 0. So it's another piecewise deal. It's going to look like this, but over here it's just going to be flat. Okay, so it says show that f is differentiable at x equals 0. So we have to do a left hand and a right hand limit. So let's do this way again. Let's come at 0 from the right. So f of x minus f of 0. X minus 0. Well, f of 0 is 0 even from the right. So actually f of 0 is 0 no matter which way you're coming because it's defined that way. So I would use x squared on this side over x. And so cancel those, and if you think about the graph y equals x, its limit at 0 is 0. And then if you come at the function from the other side, f of 0 is still 0. You use the other definition, but you use what the actual definition is, not the limit. So the function is defined to be 0. F of 0 is 0 because of this, and then x minus 0. Well, 0 over anything is 0. And the limit of a constant is 0. So because these agree, the derivative exists. So f prime of 0 exists and is 0. Now it says find f prime for all real x and sketch it. Well, f prime of x would be 0 for x less than 0, and it would be 2x for x greater than or equal to 0. And it matches at 0, so it doesn't matter which side I do the equals on. So it looks like this, and then it's still flat over here. Okay, so that was B. And then C says, is f prime continuous? Yes, because the limits match up here. Is f prime differentiable? And I think the answer is no. So if you focus on 0 here, I can do the limit out, but you can kind of see this. If you look at f double prime and just sketch what it should be for C. So f prime is continuous, yes, but f prime is not differentiable everywhere because f double prime is going to be 0 here, but the slope of a line is constant, so it would look like this, y equals 2. So f prime is not differentiable at 0 for C. And that means that this has no concavity, or no logical way to describe concavity there, which makes sense, because it's not a cup, right, either way. It's just kind of straight, then tilde bends, and that's not what we do for concavity. Alright, so that's number 9. And I think the last one is 11. And we want to now say that we're going to use x squared on the rationals. Common trick here. And it's 0 if x is not rational. I should have written irrational, but that's okay. And it says proof f is continuous at exactly one point, namely x equals 0. Okay, so we've done this before with continuity. I think maybe even the same problem. I'm not going to do the whole thing again. Use sequences. So, if you can always have a sequence of rationals going to an irrational and vice versa, but these all agree at 0. That's basically the idea. We've done that several times. Okay, prove it's differentiable at exactly one point. Well, if you take the limit we'll show it's differentiable at 0. Everywhere else, it's not continuous by part A. So by part A, not differentiable on R delete 0. Okay, so for at 0, if I want to go to 0 and I want to do f of x minus f of 0, x minus 0, well, I could do this, but how do I decide which f of x to pick? Okay, so same idea as before. I think we're going to use sequences for this. Well, we could. But how do I decide? Again, I've got a limit, and then I've got this again. How could I do that as well? A little stuck. I know what I want the answer to be, right? Because if I took the derivative, pretend I could take the derivative up here, right? So this is pretend. This limit should be 0, I hope. So I'm going to do something. Let's do a bit of a clever thing here. I want to think about this. And I want to show that this limit goes to 0. So I'm going to be weird, and I'm going to use the definition of limit. What does a limit mean? Well, I'm actually going to go way back to you guys' favorite problem. I can't remember, from chapter 3, about if a sequence, blah, blah, blah. That didn't make sense. Just watch me. Okay, so the limit definition would be you have this thing, and you want this thing to have a limit of 0, right? So this is like f of x minus L for limits. An absolute value. The absolute value is the key part that makes this work. Okay, so f of 0, 0, 0, 0, so you get f of x over x, absolute value. Okay, here's the trick. F of x is often 0, sometimes it's x squared. It's definitely less than or equal to x squared over x, which is equal to absolute value x. And remember that x is headed to 0. That goes to 0 as x goes to 0, right? It's kind of redundant, but this whole expression goes to 0 as x does. And that's what a limit means, right? You're bringing that magnitude from both sides, unit left-hand and right-hand limit. And so if an absolute positive thing is less than or equal to 0 as it goes to 0, that tells you that this limit here, this is a convoluted problem, equals 0. So because that limit exists, it is differentiable there, and it's equal to 0. All right, that is 6.1.